Welcome back. I will now introduce you to the concept of, well, I've already introduced what vectors are, but I'll introduce you to how they can be even more useful, and we're going to use that to actually solve two-dimensional projectile motion problems. So now we can introduce a game where you just don't throw the ball straight up. You can see how far you can throw the ball, or what's the optimal angle to throw the ball at. So hopefully you'll find this even more fun, if you can imagine it, than the one-dimensional projectile motion. So everything we've been doing so far, I think you did. Hopefully, you have an intuition that the difference between a vector and a scalar is that a vector has direction, right? So a vector has, let me do colon instead, has magnitude and direction. Magnitude and direction. While while a scalar has only magnitude. An example of a vector, velocity is a vector. That's easy, they both start with v, but velocity is a vector. Why? Well, in those examples we were doing before, we said that the ball sometimes we said that the final velocity was minus 30 meters per second. And so where was the magnitude and what was the direction? Well, the magnitude was 30, right? And the direction was, I knew what the direction was by the sign of that minus sign. In that same problem, if someone asked me, what is the speed of the ball right before it hits the ground? I would have said, the speed is just 30 meters per second. And I wouldn't have to say 30 meters per second down or minus 30 meters per second. I'd just say 30 meters per second because that's its speed. I don't know what direction it's going that speed. So that's its speed. And in a general way, and you probably, in one dimension, you could say that the scalar of the same quantity, that the scalar tends to be the absolute value of the vector quantity. Right? So, because in this example, the speed is just the absolute value of this, right? If my initial velocity was plus, that's not equal. That's actually just equal. If the initial velocity was plus 30 meters per second, then the speed would still be 30 meters per second. So I just wanted to introduce that notion. And in one dimension, velocity can kind of be, direction can be implied by positive or negative numbers. But now, when we go into two dimensions, we're going to have to get a little bit more sophisticated in terms of how we give direction. So let me clear this. So let me give an example where I take a ball. I take a green ball, clearly a green ball, and I throw it. That's a straight line. I throw it at 10 meters per second, but I don't throw it straight up. I actually throw it at let me think of a good angle. I throw it at I throw it at a 45-degree angle. Or if you like radians, that's pi over 4, right? So let's say I throw it at a 45-degree angle. So now my problem becomes a lot more complicated. How do I specify the magnitude and direction? And then how do I solve this problem? How do I figure out how high it goes, how far it goes, et cetera, et cetera? And hopefully that's what we will be able to teach you over the course of the next couple of videos. This is the ground, right? So if I just want to give the speed and direction, or the magnitude and the direction for this vector quantity, I have just specified it. I could just say my velocity, or my initial velocity is 10 meters per second at 45 degrees, to the horizon or something like that. So that would be a legitimate velocity specification. But it's kind of hard to deal with. So what I'm going to teach you is something very neat about vectors, is that you can actually break up a vector into I don't want to introduce too complicated terms, but into its orthogonal components. So you can say, well, something moving at 10 meters per second at this angle is actually moving at some speed upwards. It's moving at some speed upwards, and it's moving at some speed in this case to the right. Let's say in the positive direction, right? So if you imagine this coordinate axis, it's moving in the y direction at some speed, and it's moving in the x direction at some speed. And when they're combined, it's some way, you get this angle, or you're moving it at kind of an incline. So how do I figure out if I have 10 meters per second and I'm moving? How do I break that down into my vertical speed and my horizontal speed? And I'll show you that it's actually pretty cool. It's pretty straightforward. What you can do is you can actually draw a vector where the length of the vector is its magnitude. So let's draw it again. So let's say this is a coordinate axis, and that the length of this line right here is 10. The length of this line is 10, and it represents, speed or velocity, right, at this point. And we know this angle is 45 degrees. So it turns out that the vertical component of the ball's velocity would be equivalent to the length of this side, and the horizontal component would be equivalent to the length of this side. Right? And this arrow right here is the same thing as this arrow. I just translated it to the right, just so that you see that it's just a triangle. And it's just not any triangle, it's a right triangle, right? And what's useful, you could I don't want to get too complicated with linear algebra, but it's important that the two directions that you're breaking it up in are, well, they don't have to be, but it makes it useful that they are at right angles to each other, because then we can start to use a lot of our trig ratios. So let's just figure out this problem. I think you just need to see a lot of examples. So we're going 10 meters per second at 45 degrees. Well, what speed am I going straight up then? What is the straight up component of this 10 meters per second? Well, how do we figure out this side if this was just a regular triangle? If this is the hypotenuse, this is opposite, and this is adjacent, right? So let me break out some trigonometry. So, ka, toa. And if you don't remember your trig, or you never learned trig, I encourage you to go watch the trig videos that we have. So, ka, toa. So which of the trig ratios involve the opposite and the hypotenuse? Opposite and hypotenuse. So, or sine, right? And we know that sine of theta is equal to opposite over hypotenuse. So we know that the sine of 45 degrees is equal to, let's just call this my velocity vertical. I've never seen that variable used in actual physics classes, but I think it makes sense. This is the velocity vertical, and this is the velocity horizontal. And later I'll introduce more conventional conventions, but that'll do us for now. So my vertical velocity, or the velocity that I'm going straight up, is going to, well, sine of 45 degrees is my vertical velocity over my kind of angled velocity, right? This hypotenuse over 10. And what's my horizontal velocity? And so if I were to solve for vertical velocity, I get vertical velocity is equal to 10 times the sine of 45 degrees. And then similarly, my horizontal velocity, this is the adjacent over hypotenuse, adjacent over hypotenuse, so it's cosine. So I could say cosine of 45 degrees is equal to my horizontal velocity over 10. Or my horizontal velocity is equal to 10 times the cosine of 45 degrees. I'm about to run out of time, so I'm not going to continue this in the next video.